Hi everyone, this is John Wen. Today is June 17th. I will record the third video of the PMP problem today and continue from last two videos. We were talking about to use a brute force strategy or the Tarjan algorithm to find out the strongly connected component in order to find out the proper assignments to make the formula true on either 3 SAT or 2 SAT problem. And today we're gonna continue this project, and we will use Tarjan algorithm again, but we will draw a graph based on the 3 SAT formula. So let's take a look at the code. So in the main method, and we will hard-code a string of the 3 SAT formula, and then we will use the formula 3 SAT parser as we talk about it in the first time video, and it will parse the string of the formula into the variables, literals, and classes, and in order to let the program to know which one to take and then to do the calculation or to put in the algorithm. So today I think we will mainly focus on this class Graph 3 SAT. I think this is the most important one in today's video, and also this is where I spend most of my time to figure out what is going on inside. So let's take a look at this class. So in this class, we have two function constructor, and this one is what we will use because we pass a formula here inside, and so we will set this set this formula to the local private variable, and we will also get the size of the literals. Basically, we have here we can see we have three variables, and we have six literals in this formula. So here we can see the size of the literals will be 6. So n now will be 6, and we'll also count how many nodes will be in this graph, because we know our graph will be a skew symmetric graph. That means we will take every literals, and we also have the negative literals as another node. And in this special 3 SAT problem, we will use a pair of literals to produce nodes. So that means a pair of literals will produce two nodes. One is a normal, like the L1, L2, and the second one is a negative L1, L2. So the total number of nodes will be NL times NL times 2, because we are skew symmetric graph. So the total number of nodes will be 72, and we will also define a list array, because we will use a Tarjan algorithm again to find out the strongly connected components in later work. So here we will also initialize every array list in this 62 list array. And let's go on, continue the code, and here we will get every class in the class set, and then we will get the literals in the class from each class, and we will also get the negative class because we have a function that's negation, and this will take the will flip the value whether it is negative, and it will become the positive, but if it is positive, and it will become the negative. So basically this is we'll have 6 literals here for each class, and here we will take a pair of a pair of the literal and to find an index for them as a node. So here is what we will pass to this function as add edge. And firstly, we will take, because in this type of edges, this is type 1, 2, and we will find out the negative L1 and negative L2 to point to the L3, L3 on this function. And this is basically like the decimal or the binary numbers. This is similar to its 10th digit, and this is like the last digit of a number. So in the 10th digit or in the nth digit, and we'll times nl, so get the total value and plus the last digit to get the whole value. So here we know ngl1 is a negative of the minus x, and basically it is 1 here, and it will times 6 and plus the negative L2, and same as L3 here, and it will times NL for the first number, and then we'll plus the second number. And let's take a look at the this function, what's going on there. So in the add edge function, and basically we will have two index input. Remember, we have a pair of literals to symbol each node. So basically I and J is it stands for the combination of two literals. So here we can see we will add the J to the adjacency list of I. That means to in the graph they will be connected. And here we will use a function called edge to string. The input will be the I and J index. So let's take a look at this I and J. Let's take a look at this edge to string function, and this function will returns index to label function, and take the I and the J as input, and to give them a symbolize to same as an edge symbol. So let's take a look at what is going on here. So in the index to label function, and we'll take a single input as index, and it will basically get the two basically we'll get to get two literals output, because remember in the input we just input one index, but actually we symbolize two literals compilation. So here we will reverse to get back the two literals from the index, and then to put them in a string and return this string to this function. So this is basically edge to string. That means we will take the index number of two nodes, and then we will return a string to describe which nodes point to which nodes. So basically this is a core idea of this function edge to string. So let's go back to this add edge functions here. So basically we will add several types of the edges, and these edges will cover all. And in the first and second type, and it will push like the negative L1 and negative L2 to L3, and or the negative L1, negative L3 to L2, L2. So basically we'll take all the possibilities and including the negative of the negative literals combinations. So basically here we can see a very interesting to calculate the negative of the negative combinations. We will plus the NL times NL. That means we will flip the value by adding the positive total number of the I think here is 36. So that means we will get a flip number from the negative number. So basically this is a first and second type, and here we also will will add the edge of xy to xx and yy, and in this type of edges we will ignore the cases like the x minus x or xx by checking if the negation of x, if it is equal to y. So we will get the basically x y and to xx and yy from this loop function, and this is a third type, and we will get the fourth type either, and this one will from the xx to negative minus x y, and if the y equals x, and we will just continue to skip this rest of the code and then to find the other one, because we don't need to consider like the xx point to negative xx minus xx. So this is a case, and finally we will also get the fifth type of the edge, that is to get a negative xx to minus x for each literal x. So this will be also a loop that to get all the cases and be added to the edge for each literal x. So let's go back to the main method here. So now we get a graph 3SAT graph, that is to take a pair of literals as a symbol, as a node, and because we are skew symmetric graph, then and we will get a symmetric graph. So we will get 62 nodes in total, and now we will use the same method as the last time we talked about to get the strongly connected components by the Tarjan algorithm. So now we get a graph, and what we use is get SCCs function to get the strongly connected components. So in this function, we will use a Tarjan algorithm or Tarjan function, and to put the list we previously defined and also added to each node, and we will get SCCs from this function. So let's take a look at this, review this function again, and basically it will use a DFS and begin from the arbitrary nodes, and any node will be only visited once, and we will update the low link value along the. So here is low link value for each of them. So it will be a list of values, and we will update this value along with the DFS. And when the mean value is equal to the is equal to the is equal sorry, yes, when the low link value is equal to the mean value, that means we are back to the root of the SCC. That means a strongly connected components, and at that time we will pop up these nodes in the same SCC graph or a tree, and we will pop up from the stack, and we will continue the rest of the arbitrary selecting the start node, and then to do the algorithm again, and in order to find out all the SCC components. And here is a DFS function we will use in this get SCC function. So after we run this function, we will get the SCC list available, but at this time we will only get the index of these SCC nodes, and the last step we will convert this index into the literals again by using this SCC to SCC literals function, and to passing back to the literals. So let's go back and review what's going on here. So the input will be a list of integers. That means index of the SCC components, and we will use put them in a array, and to get back the literals of each strongly connected components, and finally we will get the components out. So basically, this is the program we will talk about today, and we focus on the 3SAT graph generation, how to create a 3SAT graph, and we will use a pair of literals instead of one, and we will make them a combination and to produce an index for each of them, and then we will use the function to get back the literals according to the index, and add them add the edge for 5 categories or 5 types of edges onto them, and then we will, after the graph is finished, and we will use a Tarjan algorithm again to get the strongly connected components, and based on this one, and we can do the rest of work by to get the proper assignments for each strongly connected components, again as the last video we were talking about. So yeah, so this is main things I learned and work on for the for past week, and hopefully we will have more understanding or better understanding on this 3SAT problem by now or by then. And okay, so this is content of today, and until next time, happy coding, and thank you for your time.